So we've already defined a zero of f of z as any point such that z0 such that f of z0 is equal to 0. The reason for talking about zeros is that, as we briefly mentioned, the singularities of a function are what we need to do this calculus of residues. And singularities are basically when you have 1 over 0. So we need to study zeros in detail. Once we understand zeros, then singularities are, so in some ways, very similar. Or the way you classify singularities is very similar to the way you classify zeros. So we talk about a zero of order m. I'm now going to give a technical definition, which is actually not, it's true, but it's actually not really the best way to show that something has a zero, is a zero of order m, but I'm giving it anyway. So if f is analytic at z0 and fz and its first m minus 1 derivatives are 0 when z equals z0, that means that at z0 you have a zero of order m. So when the first derivative at a 0 doesn't vanish, then we call it a simple zero. So basically, a simple zero, another way of putting it is if you imagine a graph of just f of x, for example, a graph of f of x, and we're talking about a real function now, graph of f of x, and that graph crosses the x-axis at an angle. So it's not tangent to the x-axis, it actually crosses at an angle. That would be an example of a simple zero, simply because the first derivative, the gradient, f dashed, at that 0, because it crosses the x-axis at an angle, is not 0. So the simple geometric interpretation of a simple zero is when the graph of f of x crosses the x-axis at an angle. Okay. In the case of higher ordered zeros, then it will be f of x will be tangent to the x-axis when at that 0. So a more useful definition of or description of a zero of order m, which is also true, is that if it's a zero of order m, then you can always write this down. F of z is equal to z minus z0 to the power m times gz, where gz0 is not, g of z0 is not 0. Okay, so the fact that f of z is 0 at z0 comes from this thing here. So that sort of makes it easier to understand in a way, that basically if m is 1, it's just coming from the fact you've got z minus z0, which is itself a straight line. If you plot it, x minus x, y equals x minus x0 or something is a straight line, which crosses the axis at x equals 0. If m is 2, then you've got a parabola. If m equals 3, you've got sort of cubic, but it's got gradient 0 at x equals x0, if you like. So then this maybe looks complicated. The pi means a product. So from then it's clear that so this is, again, it looks a bit abstract, but actually in practical terms, this is actually a very useful formula. So from this, it's then clear that if I've got a function f sub I, which has, or a set of functions f1, f2, f3, and so on, which have zeros of order m sub I at z0, then overall, if I multiply those functions together, then I'm going to get basically what's going to happen from this, if I multiply f1 by f2 and so on, then these things multiply. When I multiply z minus z0 to the power, m1 by z minus z0 to the power m2 and so on. The m's just add together. So the overall order is simply the sum of the mi's at z0. So now we get on to some actual definite examples. So for example, f of z equals cos z, a very familiar function, has zeros obviously at z equals n plus a half pi, as we've said. Now, as you realise, f dashed of z is cos z, which is not 0 at these points. If you plot cos x, then obviously when it's 0, then it doesn't have gradient 0. So these are all simple zeros. So what about cos to the power p? Well, we just apply this rule here, and if it's the power p, then it means those zeros must be of order p in the case of cos to the power p, okay, because you've got cos multiplied by itself p times, so you just add 1 to itself p times, which is p. Okay, so the zeros of order p. Okay, so question 14 you should be able to do now. Find and classify the zeros of the function z sine z times sine z. So you should find all of the zeros, describe all of the zeros, there's an infinite number of course, and say what type of zeros they are. People always say simple 0 rather than 0 of order 1. So simple 0 is a term you should know. Otherwise you call it a 0 of order 2 or 3 or so on.